In this circuit we have to calculate the current. The answer is 1.33 ampere. How we solve this is, in the bottom part you can see a collection of resistors. Let's solve that part first. Okay, each resistor is of 1 ohm. So how will you solve such a part? Let's do that part first. So that collection of resistors I am drawing first. Okay, and let's name those resistors as, say, A, B, C over here, and let's name as D over here. Okay, D over here. Now let's draw a Wheatstone bridge. And let's name these. Let's name this Wheatstone bridge with the names A, B, C and D. So this collection of resistors actually represent a Wheatstone bridge. How? You can see a resistor connected between A and B. So over here, a resistor connected between B and D. This is over here. A resistor connected between A and C. Okay, this is here. A resistor connected between C and D, and finally a resistor connected between C and B is here. So we have these five resistors in the Wheatstone bridge. So we know how to solve the Wheatstone bridge. There won't be current flowing through this resistor, so you can neglect the resultant resistance. You can easily calculate that will be 1 ohm. So the entire circuit, this entire part will be reduced to 1 ohm, and these two voltage sources will be, the resultant will be 2 volt. These two voltage sources, the resultant will be 2 volt. So how the circuit will be reduced? The circuit will be reduced like, you can draw a 2 volt, a resistor over here, 2 volt, and a 1 ohm, like this. And now you can solve this easily. Okay, how will you solve this? You can use Kirchhoff's method, or you can use the direct formula method, sigma E divided by capital R plus sigma R by M. So sigma E means total voltage in a branch, which is 2 volt, divided by capital R is 1 ohm, 1 plus, what is the equation for? The equation is for current. What is the total resistance in a branch? It is 1 ohm. So 1 divided by number of branches, you can see it is 2, excluding the main resistance branch, number of branches is 2, so 2. So the answer will be 2 by 1.5, which will be equal to 4 by 3, which will be equal to 1.33 ampere, which you can see over here, which is 1.33 ampere. Thank you. Hello all, I'm going to show you how does a capacitor work. So here you can see a parallel plate capacitor, and here you can see a battery. Right now I will connect the capacitor to a battery of 0 volt. What will happen? Nothing will happen because the voltage is 0. I'm going to slightly increase the voltage. You can see the charges are now getting distributed on the capacitor plates. What will happen if you increase the voltage of the battery? The charges will come more and more. What will happen if it is the maximum voltage? Maximum charges will get distributed on the capacitor plates. Now let's disconnect the capacitor plate from the battery. What will happen? Nothing will happen. The charges won't get discharged. But in a real situation, if you do this, the capacitor will slowly discharge through air. This is a simulation where you can't see the charges getting discharged through air. Now let's connect this to a bulb. What will happen? The bulb will glow. Why? Because the capacitor stores electrical energy. That energy is now transformed in the form of light and heat. Capacitors store charge. It is a charge storage device. If you disconnect and reconnect to the battery, once again the charges will get stored in the capacitor plates, and again if you shift the terminals to the bulb, once again it will glow. This is the simplest working principle of a capacitor. Thank you. Good morning all. I'm going to show you the working of a Zener diode. Here you can see a source. Here you can see a Zener diode, a dumb load or dumb resistor, a household resistor or an electrical load. What is happening here? The Zener diode is acting like a stabilizer or a regulator. Whenever the voltage across the input is changed, the concept is that the voltage across the Zener diode should remain constant. Here the diode which I have taken is of 10 volt, so the voltage across the Zener diode should remain as 10 voltage. The remaining voltage should be dropped across the dumb load. Now let's change the input source to say some 60 voltage. What you can see is that the voltage across the electrical load is still remaining as 10 volt, and the voltage across the dumb load is now reduced to 50 voltage. So keeping the voltage across the electrical load constant, the entire remaining voltage is dropped across the dumb load, which means it's a power consuming circuit. It's not a power saving circuit, but still we have an advantage of regulation or stabilization. So the remaining power is actually dissipated as heat, but that's fine. Here we are getting an advantage of regulation and stabilization. More regulation circuits are there in power electronics part, where you can use thyristors and advanced switches in order to control the voltage. Here this is a basic circuit, that's why it is becoming a power consuming circuit. So more than that, we have a lot of other information to learn, which is changing the voltage keeps the voltage across the electrical load remain same. Okay, that is why we should use a stabilizer. Any kind of lightning or over voltage or over current issues keeps the voltage across the electrical load remain same, and the remaining voltage will be dropped across the dumb load. Hope you understood the concept. Thank you. This is a full wave rectifier circuit where you can see the source, you can see 4 diodes, you can see an electrical bulb, you can see a capacitor and a switch connected over here with a voltmeter across the electrical load. So what is a full wave rectifier? A device which converts AC to DC. Right now I'll show you the graph of the source. The source is an alternating voltage which is having a 50 Hz and 230 RMS. Now this we have to convert into DC. So you know the working principle. This is not what I'm going to explain. What I'm going to show you is exactly how the current flow. So every time the current is flowing through the same path through the bulb from top to bottom. You can see that. And that is the advantage, and that's exactly why we are getting it as DC. So the current is flowing through the same path, making AC to DC. So let's see the DC waveform or the output waveform without a filtering circuit. So if there is no filtering circuit, what you can see here is the pulsating AC or pulsating DC. You can see only pulses. A lot of harmonics are there. So it's not still a DC, pure DC. What we need is to make it a DC is that we need to filter this harmonics or higher frequency. For that I have connected a capacitor in series with a switch, where once you turn on the switch you can see what will happen is that the output is now more over a DC. Okay, so let me turn on the source once again. You can see the shift now. Okay, now that output harmonics are gone, disturbances are gone, noise is gone. Now it's a pure DC. This is how we rectify an AC to DC. Okay, now you can adjust the capacitor value so that you can change that DC waveform. So right now this is how a full wave rectifier works. Hope this is clear. This is an LC oscillator. Those who haven't ever seen an LC oscillator working, let me help you how this functions. Here there is a source, a capacitor, a resistor, an inductor, and a double throw switch. So what I just did is that I just clicked the switch and now the capacitor is fully charged through this circuit. Hope you can see this circuit. Okay, so the capacitor is charged through the source. Now once I click this switch button again, it will flip into the other side where the inductor is connected. So once the switch is connected to the inductor side, the L and C, the LC becomes a series circuit and there will be oscillation. And since this circuit simulates a practical case, not an ideal case, there will be damping. So definitely the oscillation will not persist forever and it will damp. Let us see how it works. So you can see the oscillation is damping. Yes, there is oscillation, but it is getting damped. So once I flip the switch back to the capacitor is charging, and once it is fully charged, when I reconnect the switch, you can see the damping. This is the working of an LC oscillator, which is helpful in many electrical circuits where we need sometimes electrical energy. We use this LC oscillator instead of a battery, where it can give a sudden supply of power. Hope you understood this. Thank you. This is a circuit with a 10 volt DC source and a 5 ohm resistor. The current flowing will be 2 ampere. We know that. What we are going to discuss is a situation where there will be current without voltage. Ohm's law says that voltage will be proportional to current and the constant of proportionality is resistance at constant temperature. How can there will be current without voltage? Let me take this circuit onto a white screen. Here, let me name points as A, B, and C. What we are going to focus is on the conductor AB. We know that current flows through the line AB, but the voltage difference between A and B, we know it is 0. VAB, we know it is 0, but still current is flowing. How it is possible? Let me take Ohm's law, which is V equal to IR, and let me take the resistor here, which is 5 ohm. The current flowing through the 5 ohm will be equal to the 10 volt voltage difference across B and C, and 5 ohm gives you current which is 2 ampere, which we have already seen. Now if you take the same Ohm's law V equal to IR in the case of AB, we know that the resistance is definitely 0 because it is ideal. It is not a practical case. In a practical case, every conductor will be having a resistance, and here the current flowing is 2 ampere, 2 ampere, still the voltage is becoming 0. So yes, current exists without voltage. This is a very good example to show you that current flows through a particular line even though there is no potential difference. Okay, so such situations exist. Thank you. Which of the following quantities is the same for all ideal gases at the same temperature? This was a question asked in the previous exam, correct? And the answer marked was the number of molecules in 1 mole. So a question was asked back, why not the option number A, the kinetic energy of 1 mole? Because we already have studied the formula for kinetic energy, correct? In the formula for kinetic energy, we have studied it as 3 by 2 RT for 1 mole. So let me make it very clear. You can see the simulation over here where I have introduced heavy particles and light particles. I have introduced 50 count for heavy particles and light particles. And here you can see the kinetic energy graph where even though the count is same, okay, even though the count is same, the temperature is constant 372 Kelvin, the kinetic energy is slightly varying. The reason is because they are continuously colliding on the walls. So theoretically it is same. Theoretically it is same. Practically when you analyze the kinetic energy of gases, you won't get a steady graph. At the same time, you see the average speed. The average speed is definitely more for the lighter particles, and we have studied the formula for it, which is root of 8 RT by pi m. Okay, so and that's exactly why the option 3 was correct answer, which is a universal constant, which we normally say as Avogadro's constant, Avogadro's number, the number of molecules in 1 mole. But the kinetic energy of 1 mole, even though it is theoretically correct, practically when you analyze, it will not be a constant, which is what you are seeing on the graph. And that's why option C was correct. Here you can see a coil, a bulb connected to it, and a bar magnet. We all know what is going to happen as you introduce the bar magnet into the coil. What will happen once you introduce the north pole of the bar magnet into the coil? Definitely the bulb will glow. Fine. Now I am going to take completely that bar magnet through the other side itself. So south will be leaving. Once again the bulb is glowing. I don't know whether you noticed the direction of the needle. So I'll do it again. I'm going to introduce the north pole of the bar magnet into the coil. Check the direction of the needle. Okay, direction of the needle is going towards left. Now I am going to take the south out from the coil. So direction of needle is towards right. I'm going to insert south into the coil from the other side, from this side. So south, when I introduce, it's going towards left. And once I take the bar magnet out entirely from the coil, that means north taking out from the coil, you can see the needle going towards right. So that is the case of a single coil experiment. Once I introduce two coils in which one is having lesser number of turns, what could be the expected result? The expected result will be the brightness of the bulb. In the case of only two turns, you can see the brightness is reduced. See, the brightness is reduced. But in the case of much number of turns, the brightness is more. You can feel the difference now itself. Understood? So brightness is decreasing or increasing depending upon the current that is flowing. Current means induced current. So whenever you introduce a bar magnet into a coil, actually electromagnetic induction is occurring, and that induced current is actually flowing through it, deciding the brightness of the bulb. Okay, so introducing field lines, you can see from north to south field lines will flow, and this is just to show you with field lines, nothing much other than that. And in the case of two turns, you can see the brightness is less compared to the previous case. Okay, so that's how you need to study a particular experiment. Via simulations you get a much better idea. I'll be introducing more simulations in the next classes. Okay, so I believe you understood today's class properly, and we will be discussing more questions from remaining chapters in the next capsule classes. Okay, thank you. Okay, so let's do some simulation. You were doing a lot of problems for the last few days continuously, so let's try this simulation. This is the Pascal's law simulation. Pascal's law simulation, what you can see is that two conical vessels with different area of cross section altogether, and you can see two barometers in order to calculate the pressure. You can see here the right now pressure is almost equal to atmospheric pressures because there is no water inside it. So it's showing some 1.01 into 10 raised to 5 Pascal or 101 kilopascal in both places. So let's fill the water and let's see how the pressure will vary. So what is your expectation? Let me, if you turn on the pipe which is kept at above, what will happen to the pressure? That's what you should first keep it in mind. Once I pour more water, you can see that the pressure is steadily increasing. This is because of the fluid pressure also happening. Okay, the fluid can cause a weight or a force, we can or a pressure. That pressure is the hydrostatic pressure, which is HROG. So along with the atmospheric pressure, the hydrostatic pressure is also acting on this, and thus the pressure is increasing. And what you can see is that if you just let the water go out from it, the pressure will come back to the normal atmospheric pressure. Okay, so if you increase the density, let's increase the density, fluid density I'm increasing. Let me take honey instead of water. So what is your expectation now? What will happen to the pressure this time? The pressure should definitely increase, correct? See, if I fully fill it, full 2 vessels with honey, you can see that the pressure is increased. Something else you should understand from this particular simulation is that both conical section is having different area in the bottom, and still it is having the same pressure, which is the Pascal's law saying. Okay, because it is a continuous liquid system. Understood? It's a continuous liquid system, and it obeys all the laws, and it is having no viscosity over the surface. So it's a Newtonian fluid. So we have to treat it as a Newtonian fluid, and we should not take any non-Newtonian fluids for this particular experiment. What is the difference between Newtonian fluid and non-Newtonian fluid? That you can apply a stress in the non-Newtonian fluid, where you can't do that in the case of Newtonian fluid. For example, you can take the case of a toothpaste or a hair gel for non-Newtonian fluid, or ketchup for non-Newtonian fluid, but the case of water, it's purely Newtonian fluid. Got it? For this kind of experiments, you have to take only Newtonian fluid, and you can see the pressure is being the same on both cases, and that is what we also call as hydrostatic paradox, which is the application of Pascal's law. So now it's showing the pressure, which is 142 kilopascal. Let's drain this honey out and let's fill with water. So let's fill this with water, back to water, which will be having near 1000 kilogram per meter cube density. So once you fully fill this with water, you can see the pressure is less than compared to honey. Now it is only 130 kilopascal. The reason is because the density is low. HROG, the rho factor, even though the height of the vessel is same, gravity is same, you can see that the pressure is definitely low compared to that of honey. Now if you go to Mars, planet Mars, what you can see, the pressure is decreasing. What's the reason? Gravity is less. So yes, this time height is same, we have density the same, but due to the decrease in gravity, acceleration due to gravity, the pressure is much less. And once you jump to Jupiter, what will happen? The pressure, in the case, if you simply go to a small height below water, you will be crushed, because look at the pressure, it is 331 kilopascal. Understood? So the gravity is making a huge influence. Okay, gravity is making a huge influence in the case of even the pressure due to liquid also. So along with the atmospheric pressure, the pressure due to liquid is also very important, and thus we studied this simulation with respect to some concepts like hydrostatic paradox, which is the application of Pascal's law, as well as here you can study the pressure formula also, and how it varies with respect to gravity, then fluid density, etc. Okay, so this is the final simulation, and this is Wayne displacement law. Wayne displacement law means for any black body, if you take the temperature of the black body is inversely proportional to its wavelength. So if you consider, imagine sun itself. Okay, right now you can see on the right hand side, you can see the temperature scale is on the sun's point. So if you increase the temperature, what you can see is that the wavelength is reducing. So if you decrease the temperature, you can see the wavelength is shifting towards right, means it is increasing. This is what exactly Wien displacement law is saying, that for any black body or the black body radiation, okay, the wavelengths that is emitting out by a particular black body, which can be a star or anything like a light bulb or any hot substance which emit light in the form of electromagnetic spectrum, there this particular theorem will work out. It says that we can calculate the temperature of that black body from its wavelength. Okay, that's exactly what this theorem is saying. And if you increase the temperature, you can see the wavelength will be decreasing, and if you decrease the temperature, you can see the wavelength is increasing. That means any object which is having a very high temperature will be emitting light of shorter wavelength, something that is towards violet and indigo from the VIBGYOR spectrum. And any body which is less hot, okay, something like light bulb or the case of earth which emits radiation, that will be shifting its wavelength towards the red spectrum. So that is how the black body spectrum itself will work out, and that's what Wien displacement law says that, and that's what Wien displacement law is saying. And there is a constant, Wien displacement constant or Wien's constant, and the value is 2.897 into 10 raised to minus 3 meter Kelvin is the Wien constant for that. Okay, so that ends up the simulations, all 10 simulations. I hope you understood. So with the Wien displacement law, let me conclude all the simulations. Thank you for listening.